You can start.
Yeah? Okay. So the form that we have here for the wave function is defined in this fundamental domain D2 that we had with the specific ordering of the particles x1 less than x2. Now, for the extension to the whole of R2, which is really our Hilbert space here, it's completely trivial because we invoke symmetry of the wave function. So Bose symmetry forces us to have a completely symmetric wave function under particle exchange. That means we can explicitly write the wave function of psi 2 in the whole of R2 as the following thing. So you just kind of looked as a sign here when we change x1 for x2. So let's just encompass this in this form here. So we just have a sine of x2 minus x1. Okay, and then we'll just write it in this way: e to the I k1 x1 plus I k2 x2. And then what I will write actually, I will which way am I going to write it? I'll write it like this. So minus I over 2 sine of x2 minus x1. Okay, I'm sure you have good eyes, you're young people, you can still see this. Okay, times, so this thing here has the phi of k1 minus k2, which I will write as k12. Okay? So k12 is k1 minus k2. And then, of course, there's the other part where you just have the momentum permuted, the I k2 x1 plus I k1 x2. Then plus I over 2 sine of x2 minus x1 phi again of k12. Okay, so remember the phi function is antisymmetric, so phi of k21 is just minus phi of k12. Okay, so sometimes later I'll flip that. Okay, so or more aesthetically, just in a more succinct notation, we will have that this is the sine of x2 minus x1 times the summation over permutations of the twofold permutation group. Okay, so 2 with the signature of the permutation. Okay, so you understand that? So this is really the signature of the permutation, so the number of two-element permutations you make to get to the general permutation of e to the I k p1 x1 plus I k p2 x2, okay, times, let me write it here, times e to the I over 2 sine x2 minus x1 times phi of kp2 minus kp1. Okay, so yeah, it's just kind of playing on the limits, but okay, so this is the form of the beta ansatz. So look at the signs here. So you have a set of quasi-momenta, k1, k2, k3, up to kn. In this case, just up to k2. And then you can distribute these quasi-momenta in n factorial ways on your particles. Each of these possible applications of the set of k onto the particles leads to one term in your wave function. And all these terms are linked together with very specific relative amplitudes that are given by twofold phase shifts when you permute particles, if you want. Okay? So this is a kind of full beta ansatz for the two-particle case, right? So this is okay. So this completely this is a legitimate wave function at this stage for any k1, k2 because we haven't we're just still working on the continuum here. Okay, now there's one property of this wave function which is important. So property. is that if you take psi 2 of x1, x2, and then you do k2, k1, okay, then this is minus psi 2 of x1, x2, k1, k2. Okay? So, there's like a Pauli principle at work here, in the sense that immediately we notice that if we try to give the same quasi-momentum to the particles, the wave function vanishes. Okay? It's not a normalizable object anymore. So you are not, so two particles cannot have the same momentum. In a sense, you can, I mean, so you just, you fail to solve the Schrödinger equation when that's the case. You get a non-normalizable wave function. In a sense, the way you do it is that two particles, they have the same momentum, so everywhere in space, they are in phase with each other. Okay, so in a sense, any interaction that you put in there will lead to an absolute disaster, because they will always be together, and the interaction effect is just going to completely kill off your wave function. So these are not allowable states here. Okay, so that's the first restriction. Now, so that said, there's a lot of stuff in the literature about this anti-symmetry, that it's a fundamental thing about these wave functions. Okay, actually it's not. Right? So you read that in the books. The wave function is anti-symmetric. No, that's not a correct statement. The correct statement is that the wave function is chosen to be anti-symmetric with respect to these things. Because I might as well define another function, okay? So let's call this one the anti-symmetric one. I can also define a symmetric function. Which is simply sine of k2 minus k1 times the psi anti-symmetric. Okay? And then I get a symmetric function when I permute k1 and k2. Okay? So, in fact, this turns out to be the more natural choice once you have learned the algebraic beta ansatz. Okay? But this is just a little technicality for the wine tasters in the audience, right? So, but anyway, so that's the thing. This anti-symmetry of the wave function in permutation of the momenta here, it's a convention. Of course, the vanishing of the wave function with coinciding quasi-momenta, pairwise coinciding momenta, is a feature that remains. Okay. However, it is the symmetry versus anti-symmetry is a question of choice. Okay, that's maybe for, maybe you'll never use that. Okay, now what we've done essentially is that we've given the template for the wave functions of two particles on the line. Now the first generalization that we would like to do is to consider an arbitrary number of particles. Okay, so let's just do that very quickly. If we now consider many particles, okay, so solving the Schrödinger equation is equivalent to solving the following system. So you would essentially define a Dn, which is just a domain where you order all the particles. Like this, okay? And this would have boundaries at all slices where two of the coordinates coincide. Okay, so solving the Schrödinger equation in Rn then becomes equivalent to solving the Schrödinger equation in this Dn domain, which you can do because it's just, again, free waves, products of plane waves, just n factorial of them that can be combined together, complemented by the many particle generalization of the boundary conditions that we have. Okay, so essentially what you what you have is two equations to solve. You want to solve the n particle Schrödinger equation. Okay, in Dn. And then you want to solve the boundary conditions dxj plus 1. Can you still, let me just move this up a tiny bit. So dxj plus 1 minus dxj minus c psi n evaluated on the slices where x, sorry, so evaluated on the slices where xj plus 1 minus xj is equal to 0 plus. This thing is equal to 0. Okay, so this is just the many particle generalization that we have. If we solve these two conditions here, then we get the psi n here in domain Dn, including its boundaries, and therefore, by Gauss symmetry, we extend that to the whole of R. Okay? Now, of course, the magic is that the logic that we used for two particles is immediately sufficient to solve this n particle problem, because we only need to make sure that at every possible coincidence we have the right form. But as long as within this n-body wave function we have a kind of part of the two-body wave function that does the right thing for this choice of two coordinates, then we're okay. Okay? So the generalization is completely straightforward. So the solution is the beta ansatz that the n particle, so let me actually write even the final form after we've re-extended it to the whole of Rn. Okay, so here there's a psi n, which depends on n coordinates and n momenta. Okay, and this is, well, let me specify it. So this is going to be in the whole of Rn. Okay, this thing is equal to, we have some signs here, so let's just do it in this way. So product n, let's do it like this, j1 greater than j2 greater than or equal to 1, sine of x j1 minus x j2, sine of k j1 minus k j2. Okay, see what I mean? Times the summation of permutations now in the n-fold permutation group of -1 to the signature of the permutation times e to the I summation j is equal to 1 up to n k pj xj. Okay, so these are our free waves. But then there's this phase here, which is I over 2, again summation j1 greater than j2 from 1 to n of sine of x j1 minus x j2 times phi of k p j1 minus k p j2. Okay, a big mess, but it's an exact n-body wave function for the Lieb-Liniger model. Okay, it's at least the template. In fact, it's the form of all wave functions of the Lieb-Liniger model. Okay, so you see you have a wave function which is a mess because it is a sum over n factorial terms. Okay, and that's kind of a fun comment you can make about the beta ansatz, because the beta ansatz is named after the form of the wave function. Okay, and many people over the last 8 decades have worked with beta ansatz, but I think it's almost a fair statement to history to say that nobody has ever derived anything useful from a beta ansatz wave function. Okay? So it's extremely difficult to do anything with the wave functions because they are such large summations. They are summations over these n factorial terms. Of course, there are exceptions to this. Now, so you can look at the literature and find people who calculate actually things with explicit expressions of beta wave functions. But this is not the bog standard way of operating. The reason why it's so useful is because we know we are in the possession of eigenstates, but we know their energies and their momenta. If we know the energies, then we can do equilibrium thermodynamics. Okay, so we will be talking about that. The most straightforward thing you can learn how to do with, theory of beta ansatz is to look at equilibrium thermodynamics, because then you never play with wave functions, you just play with energy levels. Okay, and that we'll do quite a lot of that. By the way, so the energy of such a wave function, trivially, so En is just the summation. Okay, and the momentum of this is just the summation of the kj. Okay, so yeah, maybe just a little comment. Of course, these k's here, they are not physical momenta. Okay, they are internal labels for the wave function. There is no operator that will have as eigenvalue kj. Okay. So only the total momentum, which is related to translational invariance of the whole system, is a good operator. Okay, so these kj are really the labels of our wave function. Okay, is that all right? Any questions at this stage? You kind of phased by this n-body thing, or you worried about it? Actually, the generalization to n-body things is slightly less trivial for the spin chain. So maybe Martin will spend more time explaining this, or not, I don't know. But okay, it's, in the case of the Bose gas, it's completely straightforward. Okay, so let's just move on to the next theme, because now we've been dealing with the states in the continuum. Okay, that means we have an infinite line. That means that irrespective of how many particles I throw on this line, I will, in a sense, always stay in the limit of zero density. Okay? So actually, this is a bit bizarre, because the kinds of wave functions we can write now, the kind of well-defined wave functions here, but really they extend up to infinity, and they represent a zero density gas. So what we will do now is do like you do in quantum mechanics when you want to calculate anything. You will quantize the system by putting it on a finite size. Okay, so particles in a box, particles on a ring. We will now put the system on a ring, which means that there will now be a finite density of particles, so a finite number of particles per unit length. Okay, and that changes the physics quite a lot, actually. So in a sense, it's very important to do this. Okay, so let's discuss this now. So quantization. Quantization and the beta equations. Okay, so what we do is that we put the system on a ring of circumference L. Ring of length big L. Okay? And we will impose periodic boundary conditions. These periodic boundary conditions, so again, let's just do the n is equal to 2 case first, because that's the illustration for everything. So we have our psi 2, and now we have coordinates here x1, but what we will say actually is that if we take the x1 particle all around the system, or the other one for that matter, unchanged. It does not pick up any phase or anything. We just choose it to be identical. Okay, so the system is purely periodic with length L. Now, of course, this has dramatic consequences for the allowed momentum modes that you can have. Okay, just like the case of free system, you know, just quantize your momenta. Here the same will happen, except that the form of the quantization condition is a kind of glorification of the one that you're used to from free particles. If you just examine the two-particle wave function, substitute these conditions in there, invoke the linear independence of the free waves, you can write these periodicity conditions in the following form. So you will essentially, this gives the following conditions. It tells you that if you just do it by examination, it's really a two-line derivation. If you have I K1, now it goes through the system, so I K1L. This thing here is going to have to be equal to e to the minus, right? Minus I phi of K1 minus K2. Okay, and similarly, e to the I K2L will have to be equal to minus e to the I phi of K1 minus K2. Okay, so what's the picture of this? Is that you have your ring like this, and you have a particle somewhere, you have a particle somewhere else, and you take it around. There are two contributions that occur. Of course, when you move the particle around, you move it around by the momentum operator, it's a generator of translations, and therefore this operator you apply over length L, so that gives you the term on the left-hand side here. But as you carry the particle around, it will be forced to scatter off the particle that is already present. And we've seen that when you scatter, you pick up this phase here. Okay, so here, essentially you can write this condition as e to the ik1L times minus 1 e to the plus I phi k1 k2 is equal to 1. Okay, so this is exactly the same as a quantization condition you would do for free particles, except that you've picked up this extra scattering phase here. Okay? And of course, the scattering phase here depends on the momentum difference between the two particles. And when you do it for the second, of course, you also have the same logic. So what you obtain essentially are coupled equations for the quasi-momenta. There is no notion of independence of the quasi-momenta of particles. The presence of a particle with a certain quasi-momentum changes the allowed quasi-momenta for the other particles. Somehow you can view it as these particles hating each other. They cannot, if one has a certain value of quasi-momentum, then the others have to move a bit out, or they have to compensate for the presence of this other particle with this quasi-momentum. So these equations here are quantization conditions, which are known as beta equations. Okay, so a system of beta equations is just a system of quantization of the quasi-momenta here after imposing some form of boundary conditions onto your system. Just for the classification of eigenstates, of course, this is completely determinant. Okay, so these are the beta equations for two particles. Now this you can rewrite so equivalently. You can write that e to the I, that's an I, e to the I K1L is equal, so just replacing the form that we had for the scattering phase shift, you can do it like this, K1 minus K2 plus IC divided by K1 minus K2 minus IC, and then e to the I K2L is equal to K2 minus K1 plus IC over K2 minus K1 minus IC. Okay, yeah, just made it. Okay, so now we are looking to solve these equations simultaneously, so we'll just study that a little bit. Of course, it's a bit complicated. It's by nature a transcendental equation for the lambdas because of the presence of exponential on the left-hand side. So you cannot solve these things analytically for, periodic circumstances. I'll show you some analytical solutions for beta equations, but only after making some assumptions about the thermodynamic limit. But in the case of a finite system, number of particles here, the solutions of these equations typically is not in closed form. Okay, there are circumstances where you can actually do closed form things, but not here. So the point is that you can start about looking for K's here that fit those equations. Now, exactly as the case of free systems, it's actually more convenient to introduce quantum numbers to label our states. The way you introduce quantum numbers is by taking logarithms of these quantization conditions, and then, of course, the fact that that you can have an arbitrary phase in there will give you a kind of winding number, a quantum number, to label your eigenstates. So here, you just take logs, and what you get are equations that look like this. So K1 plus 1 over L times phi of K1 minus K2 is equal to 2 pi over L times I1. And K2 plus 1 over L phi of K2 minus K1 is equal to 2 pi over L I2, where I1, 2, there, in this case, half-odd integers. Okay? So the idea here is that you will like to classify your wave functions by these labels in terms of quantum numbers. So you give me your two favorite quantum numbers, and we will see there's going to be, given, in this case, two quantum numbers, there will be a unique solution to these beta equations for the two quasi-momenta. Okay? And then the conjecture is that the set of all possible sets of quantum numbers gives you a complete catalog of eigenstates, and therefore a basis for the Hilbert space of your system. Okay? So that's the general idea. So this is the case of two particles, essentially maybe some comments. So okay, so just comments. If I1 is equal to I2, then K1 is equal to K2. Okay, so proof, easy exercise. Okay, it's an easy exercise because the arctan function is monotonic. Okay, and therefore, when you look at the left-hand side of this equation here, it's a monotonic function of K1. Therefore, there's a single crossing point here for any given K2 solving this thing. Okay, and if you subtract these two equations here, of course, trivially, if you have that these two are equal, then these combinations have to be equal, and because the arctan of 0 is 0, it means that this is automatically the solution. Okay, so this is trivial. So slightly less trivial is the generalization to many particles. Okay, so again, what you do is that you just say that psi n of x1, and call it xj plus L, is equal to psi n of x1 xj. Okay, and you do that for every single j. Now, just substituting the form that we wrote down for the full wave function, it shows you that the beta equations are simply of this form. So e to the I k KJL is equal to product L different than J of Kj minus KL plus IC divided by Kj minus KL minus IC, and this is minus 1 to the n minus 1 times e to the minus I summation over all L of phi Kj minus, oh, I'm sorry. Let me actually read this smaller. Okay, so it's just equal to minus 1 to the n minus 1 e to the minus I summation over L of phi Kj minus KL. Okay, the summation here can be over all particles, because if I have phi of 0, it's 0. Okay? So the same thing, we have now n particles, we take one of the particles all the way around, we scatter against n minus 1 other particles, therefore we pick up this minus 1 to the n minus 1, e to the minus I, phi of all these other particles momentum. Okay, so we have this. And then, of course, we can rewrite this in log form. In log form, it just becomes Kj plus 1 over L summation over L of phi Kj minus KL is equal to 2 pi over L times Ij, where now Ij is in half-odd integers for n even, and it's in the integers for, it's in the integers for n odd. Okay, it's just a labeling thing. Again, there's no physical significance to this.
We have n quantum numbers.
Yes. Okay, so if you have an n particle wave function, your beta equations are n coupled equations. Every single equation is coupled to every single other equation. Okay, in a transcendental fashion. Okay, so once again, finding the explicit solutions of these things is not a trivial matter. Okay, but we'll do a little bit more on that. Okay, so and I've written the form of the energy and the momentum for this n particle wave function. So now the statement is that if we kind of are hopeful people, we now expect that we can construct a basis for our Hilbert space in the following way. We choose all possible sets of quantum numbers. Okay? All possible sets of quantum numbers. Sets of n quantum numbers. The condition that we have is that within a given set of quantum numbers, all quantum numbers are non-coincident. They're all different from each other. Because if two of them or more are equal to each other, then the beta equations automatically tell us that their quasi-momenta coincides, and that gives us a wave function which is identical to 0, which we are not interested in. Okay? So the hope is that if we choose all sets of n non-coincident quantum numbers, we have a labeling of all eigenstates in the Hilbert space. Okay, so the proof of completeness is a non-trivial matter. Technicalities involved in that, but you can rest assured that everything is okay. This is indeed the case. If you believe in the completeness of Fourier transforms, then you can believe in the completeness of these wave functions for all practical matters. Okay, now let's maybe, when should I end actually?
Well, 11.
Huh?
11.
I had to let them.
Yes.
Everybody ordered their lunch? Okay. So let's then carry on a little bit with some properties of solutions. To the beta equations. Okay? So we can make a number of statements, right? So theorem 1. For C greater than 0, so the repulsive gas, all solutions are real. Okay? Proof? Consider e to the I k L. Okay? So what you, whoops, this L somehow selected itself. Okay. So you can make some trivial statements. So note that if the imaginary part of K is greater than or equal to 0, then this object here, I k L, has to be less than or equal to 1. Okay, and conversely, the other way. Okay? Now what you do is that you, just before we do, also just look at K plus IC divided by K minus IC, and you take the norm of that. So again, this will be greater or equal to 1 for the imaginary part of K greater than or equal to 0, and conversely. Okay? Now if you look at your beta equations, okay, so consider a set of K's, solving the beta equations. And then what you do is that you pick up pick the K with the largest imaginary part and call it K max. Okay? So the beta equations for K max, e to the I K max L, we will just take the absolute value here, is equal to product over J of K max minus Kj plus IC divided by K max minus Kj minus IC. And we take absolute value for this. Okay? So there's a kind of contradiction between the two sides. Okay? Because, so K max is larger, so if we just look at this side here, this has to be greater than or equal to 1. Just from this side here. But of course, this one here, it has to be, so you see what it tells you is that the imaginary part of the largest imaginary part is less than or equal to 0. Okay, so imaginary so imaginary part of K max has to be less than or equal to 0. Otherwise, this thing here cannot be larger than 1. Okay? But then you do it the other way. Okay? And the k min with the smallest imaginary part has to have an imaginary part which is greater than or equal to 0. So all k's are real. Okay? So conversely, the imaginary part of k min has to be greater than or equal to 0. Okay? So theorem proved. Okay? So in the repulsive case, all solutions are real. Of course, this relies on the sign of this thing being positive. If it is negative, actually, you find solutions that have complex k. Okay? And of course, the meaning of, so just as a comment, so for c less than 0, there exists complex k, and these are just bound states. Okay, so why are they bound states? Well, because if you go back to the beta ansatz form, if you have a k that has an imaginary part, then e to the I kx will, once you've normalized the wave function, have a decaying exponential in the relative coordinates between two different particles. So this is a bound state between these two particles. All bound states in beta ansatz are essentially like linearly bound with the exponential. So it's just like a usual mass term. Okay, so that's a thing. Now, second theorem, theorem 2, which is from Yang and Yang, 1967 or 1969. So, given a proper set of quantum numbers, okay, by proper here I mean you choose the right parity for it. Is it half integer or integer, depending on how many particles you have, and they are non-coincident. Okay? In fact, choosing them on the wrong lattice is not crucial. You would still have the same theorem, but it's very important that they are not coincident. Okay? So given a proper set of quantum numbers, the solution of the beta equations exists and is unique. That's quite handy because we have really a one-to-one mapping between quantum numbers and eigenstates. Okay, so the proof goes as follows. It's an instructive proof. So you define an action, which is the Yang-Yang action, as this. So, oops. S of the set of k's is equal to L over 2 summation over j of kj squared, okay, plus summation j less than L of a big function phi here, which I'll just make it kj minus kl minus 2 pi ij times kj. Okay, so where this phi here, phi of k, is just the integral from 0 to k dk prime of the phi function that we have. Okay, so this is just 2k arctan k over c minus c log okay, you'll see it in the notes. Minus c log of 1 plus k squared over c squared. Okay, don't worry too much. Okay, so the statement is that the beta equations are equivalent to the extremum conditions that d with respect to kj of S yang is equal to 0. Okay, because if you calculate this derivative explicitly, you just get that this is kjl plus summation L of phi of kj minus kl minus 2 pi ij. Okay, so the yang-yang action is an object which lives in, it takes values in real numbers, but from a field of Rn, okay? And the extremum condition of this action are the beta equations, okay? So the beta equations are solved at the point where this yang-yang action is extremized. We haven't proved yet that it's a minimum, okay? So the first step beyond this is to now consider the curvature of S. So what we do is that we compute the second derivative. SJL is by definition the second derivative of S with respect to Kj and KL. Okay, so this is simple calculation. So it's delta JL times L plus summation over n is equal to 1 to n of 2c divided by kj minus km squared plus c squared. Okay? Let me try to fit it here. Minus 2c divided by kjl squared plus c squared. Okay? kjl is again kj minus kl. Okay, so this is a matrix, an n by n matrix that we will talk about a bit later on. Okay, now, so for any real vector v, okay, an n-dimensional vector, can show that the quadratic form, just maybe fit it, so sum over jl of vj sjl vl, okay, is equal to blah blah blah, is greater than 0. Okay, so this is done in the notes. So what that means is that if you are sitting, so this SJL is the matrix of second derivative, is the Hessian of this function. The Hessian of this function is such that if you're sitting at the solution of the beta equations, irrespective of which direction in which you start moving, represented by this vector v, irrespective of the direction in which you are moving, you will go up. Okay? Therefore, the bottom, the extremum, is indeed a global minimum. Since it is a global minimum, okay, there's no assumption that v is small here. This is true for any v. Since it is a global minimum, its bottom is unique, right? So there's a unique solution to the beta equations. Okay, this is true for the Bose gas. Actually, the proof of such statements for other models is impossible, or at least for many other models, it's not possible. For example, for the spin chain, okay, you have to be much more careful, because then there are circumstances at which choosing two quantum numbers that are equal to each other actually does give you a bona fide solution to the beta equations, okay, for complicated reasons. But I guess Martin got the contract of doing the complicated model, I got the easy one, so it's good. Now just give the harder work to the younger people. I like that. So it's nice getting older sometimes. Okay, but for the Bose gas, the statement is a theorem. If you have a proper set of quantum numbers, you will find a unique solution to your beta equations. Right? So that's the kind of theorem on which the whole catalog is built. Okay, and then for the rest I will let you go, but you can look at the notes where there is some complement on that. So by the way, maybe just one last comment, that this matrix here that we have calculated here is known as the Godin matrix, after Godin, kind of, Moses in the clouds of integrable models. And it's a very important matrix because, as you will see in the notes, if you compute the norm of the beta eigenstates, just by doing explicitly integral over all of Rn of mod psi squared, actually what you find is that it is equal to the determinant of this matrix. It's an extremely beautiful result. Okay, so the norm of beta eigenstates is ultimately given by the determinant of the Godin matrix. Okay, and there are reasons why this is the case, but this is a very non-trivial statement. Okay, so I'll leave you with that. If you have questions, I'll be around, and then tomorrow we will carry on talking much more about physical properties. We will construct the ground state. We will take the thermodynamic limit. We'll try to do some analytical calculations for excitation spectra and things like that, and we'll see how far we get. So I want to get to the finite temperature thermodynamics, and then ultimately maybe show you some much more advanced stuff in the last hour of the 6-hour lectures. Okay, so any questions before? It's too late for lunch anyway. Okay, I'll let you go anyway. Thank you.